how the generative content can be a new mode of attack. This is complementary to what we have been discussing about deepfakes. I'll give you a brief motivation about why we do this and what is the exact implication of that. And after that, I'll give you some key architectures which can be used, some ideas on how you can explore new architectures. Okay, so if you just take a look at any face recognition system, which is based on your deep learning, so this is what is happening, right? So you can replace that block with any of your favorite network, but then you would still be able to get a score, an identification person, and so on. All right, so this is just an illustration where it's typically looking at two different persons and then it's saying, okay, this person A or person B. Now, if you go to the face recognition part itself, it contains a number of different components. Right? It's very similar to what you would have for any medical image classification as well, but in this case, we are very interested in obtaining the scores. So what we do is that we capture the data, and then we do some amount of signal processing, whatever the feature extractors that you want to use, whether it's classical machine learning or computer vision based approach, or if it's based on deep networks, whatever that is, you would get some features, and those features are then used to compare, right? So once you get the score, then you say if the score is above a particular threshold, you say yes, this is the same person. Otherwise, you would say this is not the same person. Now, whenever you're thinking about this kind of system, there are a number of points which are attack points. I'll also touch upon this in the talk tomorrow. But what I could do is I could create a system which can override the signal, right? So between the camera and the time that is the features are extracted, I can override the signal, and then I can inject, instead of my image, I can inject Pranav's image. And then at the same happens with the comparison level. So I know that the score is going to be 0.7, which is my threshold, and to cross that 0.7, I can start playing with the features, which is typically the case in the case of template protection, template attacks. And template in our case is nothing but the embeddings, right? And then you have the final decision module, which is somehow related to either to authority, which could be yourself on your smartphone, or it could be a government authority who is actually verifying this one. So if the government authority is saying yes, this is the same person, and I can override that decision, and I can say no, this is not the same person, and then reject it. Okay, so there are a couple of points where you can attack. And to do any of these kind of attacks, what we can do is, like, on the top level, you have this the reference template modification, which is your, let's assume that's your Aadhaar card database, right? The Aadhaar card database is staying up there. I could go and edit the templates inside there. And in the comparison part, what I'm going to do is I cannot touch the top part, right? I cannot really access the database from Aadhaar card, but what I can do is I can change my image, which I'm sending into the database for comparison. So that is the modify probe, and the final one is modified score, which is anything that is based on the systems which are doing this decision threshold. Okay. And then in the recent taxonomy, there has also been other kind of attacks which have been discussed. One is called as leakage attack, which means if I have two databases, how much can I link each of them together? How much can I infer about one person from a database just by looking at the database, which has purely numbers, right? So that's a bit more sophisticated, bit more software-driven attacks, which we'll not talk about. But what we will talk about is the first part, which is called as the presentation attack detection, which is in the ISO standard 30107. And recently, what has been also been more popular is with the advent of this generative networks, is what we call as the injection attacks. The injection attacks is very simple. It's let's say you are giving your picture to the smartphone for a bank system, and when you're capturing the picture, you are giving your picture, but another person is getting injected into the face frame. So we saw the deepfakes yesterday. So it's nothing but the face swapping, right? So as soon as I swap the face, the camera feed is still the same, the background is still the same, except the identity features can change. Okay? So this is somehow the industry is very much interested in this injection attacks recently, but what we are more interested is in the presentation attacks. And then what we will also talk today about, or mostly about, is the how can I modify the database up in the top, right? So if I can get access to the Aadhaar card database, how much can I change inside that database, right from the time when I'm giving my image all the way to the storage part. All right. So if you can just look at a very high level in the face recognition taxonomy, what you see is you see this kind of digital attacks, you see physical attacks. So what are physical attacks? Physical attacks are nothing but the printed picture, the photo of somebody on your iPad screen, and then the photo of somebody in a mask, 3D mask, more sophisticated like silicone masks, latex masks, or even the masks that you can get in these costume shops, right? So those are all come under those kind of physical attacks. And then we saw a bit of the other part. We saw something about morphing. We saw something about deepfakes yesterday. So today we'll concentrate a bit more on morph attacks. And if we manage to have some time, maybe we can discuss also on adversarial attacks. So what will we focus? As I said, in the current context, we'll talk about morphs. We covered deepfakes yesterday, and then there are some illustrations on how each of these attacks are conducted. This adversarial attack is a very interesting domain, which we can talk about if we manage time. Good. So now I've been talking about morphing a couple of times. I did not introduce you what is morphing. Now is the time I can introduce you what is morphing. So this is how a face recognition system should work, right? So if I give two images, it should tell me who this person is. And it would be the same if you take a medical image classification system. If I keep on sending the images, it should tell me whether this image has diabetes or not, whether this has COVID or not, right? So we train the system to do such kind of classification. In the case of morphing attack, what happens in practice is that like this, right? So I have the image, which I'm constantly getting a person's name, and now I replace that image with something else, something very subtle, and suddenly the network says that this is not that person anymore, right? So now the idea of that one goes back to this particular example. So any system, as I told you, in a face recognition, we always work with the score, and the score is nothing but the threshold that we determine from training set. And then once it has been determined, I say every time there is a new person that is coming to verify, if that person crosses that threshold, then I say it's verified, otherwise it's not verified. So now comes the idea of morphing at a very crude level. Nothing with deep learning to do. Even at a simple level of image processing, any face that I'm going to deal with, it has landmarks, right? Every person has eyes, nose, and lips, and then if I can trace the silhouette around, I can come up with the landmarks. Right? This is like the rough model every face would have. Now you can have different models which are more sophisticated that will give you 468 landmarks. Some of them will give you even more landmarks and so on. But at least you can start with something very primitive, 68 landmarks. So as soon as I have this 68 landmarks, can you all imagine I can create some triangles between them, right? Makes sense? So I select 3 points, I can create a triangle between them. Yeah? So Delanoë triangulation, right? Classic computer vision. So I take the points from, let's say from here, number 36, and I can create a triangle between 36, 40, and 50. Right? So and I can create n number of triangles inside that face. So as soon as I create n number of triangles in that face, what I can say is that, okay, for this particular face, let's make a simple illustration here. Maybe I should not do face diagram, but I can just say 1, 2, 3, 1, 2, 3. Let's say 1, 2, 3, something like this. So now I create a triangle here. I create a triangle here. I create a triangle here. Then I create a triangle here, and so on. So, which means I have one triangle, one tessellated diagram for person on the right side, and I will have the same thing for the person on the left side. So what I can do, I can say, okay, replace this particular block by the block of this person. I can keep on mixing and matching, right? So typically what we do is in morphing, we try to blend them with 50% probability. I could always say that, okay, keep 70% of this person's feature and merge 30% of that person's feature. So when I do this, so what I'm going to get is that I'm going to get this kind of image. Now, if I did not show you the two images individually, you would have easily taken this person to be this one, right? Now there are some inherent factors. For instance, the hairstyle. Based on hairstyle, you might say that is the same person. I could also control some of the side, the clothing and the neck and so on. And if I hide you that picture, you can think that this person looks very similar to this one. So what I'm interested in creating is I'm interested in creating an image which looks very similar to both of the contributing subjects. So as soon as I do this, what can I do? I can achieve something like face recognition scores, everything that I'm going to plot it on the comparison scores on the graph. I see that this is subject 1, this is Pranav, this is Mahipal. Now I merge those two images together. And if I merge a lot of different combinations like this, what is the score that I'm getting? So I'm getting a score, let's say 0.6 with subject 1, and with subject 2, I'm getting only 0.1. So that means this image is not equally comparable to both of them. What I'm interested in creating an image which exceeds the threshold, which is, let's say, 0.5. So in this case, we have this score for subject 2. Mahipal also comes at 0.5 or 0.7, and also for Pranav it comes at 0.7. So now the goal of this morphing attack is to come up with this kind of images which lie heavily on that cluster number 3. So quadrant number 3, right? 1, 2, 3, 4. If you just make it as 4 quadrants, you want to achieve that one. So when that happens, what happens exactly is that I can take such a picture and then I can go and give it to the passport authority or ID card authority, and they'll give me a new ID card, which means both Mahipal can use it and Pranav can use it. Now, what is the implication? The implication is that, let's say Mahipal is blacklisted on some services, so he'll not be able to access that service anymore. But he could always use the ID card of Pranav, and then he could just pose himself as Pranav and go inside, right? So the whole idea is about this digital identity change, which means that what we are interested in eliminating the third one. So we want to verify that person on the left, we want to verify the person on the right, but if there is an image that comes in between, we want to say that no, this is not the right image. Okay, so this is at a high level, right? Looks very fine from the conceptual part. And this was the first work that was done in 2014, which is called Magic Passport. The name is also very interesting. And then a number of works were done after this. And what exactly happened in real life? Why should we really care about this one? The synthetic content creation we have seen, it gives us number of tools and techniques, right? So if it gives us number of tools and techniques, can it be really used in real life? For those of you who have not seen this one, if you upload for some passport within Asia, including India at some point of time, I don't know. Right now, maybe we have this live enrollment, but earlier it used to be the case that I would go and give my own image to the passport office, right? So which means I would have the freedom and flexibility of modifying the image and giving it to them. And then is the second part, right? There is also this. Let's say this countries on the western part, also on the eastern part, where when you're applying for visas and also on the passports, you can upload your image. So it's not only a country specific problem. And then temporary visa, for instance, in US, there is no control, right? You are uploading your own passport picture there. So now let's assume that two cousin sisters want to travel to a country, and one of them can't travel. Now she could you replace the picture with another cousin's picture, right? So those are like practical implications. It's not only at the theory level. And what is also very interesting is that there was this German activist who was called Federica Mogherini. She was, no, sorry, I said it the other way. A German activist was a journalist. She created a morphed image of a representative of European High Commission, who was Federica Mogherini, and then she actually obtained a passport of that person. So you see here on the left side, you see all the images here. Where did that mouse go? Here. So she used a combination of this image, the one on the top left, and this image here to create an image which was equally resembling both of them, something here, somewhere around here. And then with this image, she obtained the passport from the authorities. Okay, so this gives you a motivation for why we should also look at two aspects. One, how to improve the quality of this image, and the second one is how to detect the quality, detect the attack images. So what has happened in the last couple of years? In the last couple of years, there was this first generation morphing attacks, which was purely based on the landmarks. So people would sit together and then find the landmarks first and then align them. And then after that, there was a bit of post processing using Adobe Photoshop, Adobe Photoshop or any other photo editing softwares. That was very tedious. So if you have to do it for 1000 images, every image takes 20 minutes. Probably the student that is working on this or the researcher that is working on this will not be very happy. So then came the second generation, which is also in the European project, which is called IMARS, which was recently ended in February. And there, the idea was to go look into the generative attacks, generative models. I'll talk a bit about the generative models in a while, how that is being actually used. And the third part is the what we call as the generation 3 morph, which is a combination of generative models plus large language models plus the landmark refinement. And this is an ongoing project which is called Einstein, and some of the topics that I'm going to talk here are also part of that project in the investigation. Okay, now why did we go from generation 1 to generation 3? If generation 1 was already very good, I showed you the very nice image, right, in the first slide. If I have that one, why should I actually go towards the next generation? So here is an image of me and one of my colleagues, and then we tried to morph each other into one single image, and the image actually works. The final image actually works. But now, if you closely notice that, what is happening is that there is a lot of artifacts, right? My hairstyle is different from his hairstyle. I'm wearing glasses, he's not wearing glasses, and so on. But you see that although you get a good image, you still see that there is a shadow effect there on the top, right? So the final image that you're going to get will not be of sufficiently good quality. So what you need to do is that you can sit and manually process that, use some editing softwares, and nobody wants to do that. So people want to generate large data set using simple techniques. What they've been doing is like trying to establish how we can create better morph. And as you can see here already, there is a bigger problem, right? I can't go randomly and merge my image with some female because our structures will be different, our facial features will be different, right? So which means that we have to now carefully select these pairs. So I can't also combine myself with, let's say, my pal, right? So we have a different facial features, although the ethnicity is the same, but still there are subtle things that are very different. And then comes the third factor, the age. I can't really morph two persons who are one is of 20 years, one is of 60 years. Then you're not going to succeed in fooling the passport officer and also the border control officer, right? So there are a number of things. So what can we do now? So this was another work that was done in our group, and in this case, the student did a wonderful work where he took the face recognition system, which are trained using deep learning networks, deep neural networks, and then he said, if the latent space is very similar, that means they should lie in the same angular space. You remember yesterday we spoke about the angular space, the cosine distance between two particular vectors should be very close, and the idea is also holds here, right? So if I have 20 of you, if I'm going to compute the embedding distance between each of you, then I can select the top few, which says that, okay, these two people are resembling to each other. And when I say that, that is at the high level. Now what I can do is I can also introduce other factors, right? I could say that, okay, introduce the age factor, introduce the gender factor, introduce the ethnicity factor, skin color, and so on. By integrating all such things, what we realize is that the attacks become much more strong. If you see in this whole picture, there is nothing magical happening, right? The only thing that's happening here is that the score is being computed, and once I get the score, it's a cosine distance, and then I can say that, okay, these two pairs I can merge. By doing so, what I achieve is that the images that were not able to successfully attack the face recognition system now can suddenly attack in a better way. You see the average performance was high for all the combination across different kind of morphing approaches. Okay, so here is the idea of pre-selection of the pairs, which probably would be very similar to for your selection of your training data set and so on. Okay, so that was the motivation, right? And then we spoke a lot about GAN in the last couple of days. We have been talking about the latent space, how we can merge them, how we can manipulate them, and so on. Now came the first work, which is called Morgan, which was published in 2016, if I'm not completely wrong. So the idea here is that we have two latent spaces from any deep network, right? Any of your favorite network, you extract the embeddings, and then you get a set of features. Let's call it as x1, z1, and z2. Now, as soon as I have z1 and z2, what I can do is I can simply combine them. As simple as taking an average, z1 plus z2 divided by 2, that will give me a score. So which is exactly what is happening here, right? If I set the alpha value to 0.5, so what I'm going to get is that 0.5 and then 0.5, right? Or if I set alpha value to 1, then it becomes one subject will be retained, the other subject will be gone. Now what I can do, I think there's notation mistake in that, it should be 1 minus alpha. Alpha and 1 minus alpha. And then as soon as I have that, then I get a new latent space, which is the average latent space. And now that you're all very well aware of the the encoder-decoder network, take that latent vector and then reconstruct the image back. So by doing so, you can see in the bottom part here, you start with the image on this side, the first person, and then here is the second person on the left side. Now you can start seeing the person, the appearance of the person changes from A to B. See, when it slowly goes from this side to this side, at some point of time, it's equally likely to both the people, and then comes the final output, whatever you want to choose. Gives an idea, a high level idea of how we can go from avoid the manual labor and then go towards something more GAN specific, which is in latent space, and then still use the decoder network to reconstruct it. Okay, good. So this was the first work on using the GAN, and then in our group we took it further, and then we said, if you take the images from left and right, let's focus on this image. So if I take the subject here and the subject here, two represented in green color. Now if I combine them using any other approach, you see that the person that is coming here is not very similar to this person. It may be somehow similar to this person. The same thing here, right? If I combine this person and this person, the resulting image is coming somewhere in between. So this one is more closer to this person. So which means it's not taking the identical features of both the people into account. So what we did in that case was again going back to the GAN, not doing much of the changes. Now taking the network which extracts the embeddings for me here, which I call it as latent vector or the latent predictor IL1, and then I have the other one which is giving me L2. Now as soon as I have these two L1 and L2, what I can do is I can take an average, L1 plus L2 divided by 2. Simple morphing technique, right? So 50% contribution from both of them. Now the new vector that I'm getting here, I could now start pushing it through another network, another encoder network. So from this encoder network, I'm going to get a final image, which is here. Now this image is not very realistic also, right? I mean, it has some limitations. So what can I do now? So I can now take this one and I say, okay, look, I think this image is fine, but I still want to improve the identity features, and then push the network back and then keep on updating it as long as I get better image. So here comes the idea of GAN, which is both first the decoder part, which is extracting the embeddings and then encoding them, reconstructing them, and then updating it constantly. And in this case, the idea was that the loss function that we had in the state of the art would not work. So we had to introduce some new loss functions, which would make the identity features to be more intact. So by doing that, what we could do is we could now suddenly get better quality images here. But then there are some small problems. For instance, now if you look at this image very closely, can you notice there is some artifacts near the hair? Yeah, and this is also here, right? Which is exactly the problem that we spoke about yesterday. When we are doing GAN-based reconstruction, there is always some kind of signatures that remain, and this remains here. Okay, but from the point of usage of this approach, it has a broader implication. I'll show you the broader implication here. Now, this was one of the application, one of the demonstration that one of my student did. So in this case, what he did was he took a bunch of database of celebrities, and then he started putting my image using some pre-selection technique, and then suddenly I had a new set of morph from me, and here you see that. I don't know if you are able to identify the second person here. Salman Khan, you have very good eyes. so, so what does this actually mean now, right? So suddenly it means that I have all this publicly available data set, millions of images, and I can create new set of training data for my detection approaches. So one thing is, it means that there is no guarantee that none of your some of your face images will be used by somebody who you don't know at all. So anything that is available on the network, you just take it, dump it in this kind of models, and you get a new image, and that can be misused, right? Okay, so you have I showed that how the architecture can actually have a broader impact, and the same applies for many other generative models. Okay, and then here I think one of our colleagues already identified that it was Salman Khan, so it's still not keeping the identity features very well. Okay, so we need to fix this, right? So we need to avoid that. If she's the police officer there, I'm sure that I'll never be able to cross the borders. No, I think I saw the image over there. In the top as well. Yeah, from there. But you didn't see it in the combined image? Probably couldn't have recognized from there, but Salman's image was there. Yeah. So if you happen to see the image with reference to the other image, it's still possible that you will find me, right? So now I have to fix this one. So I want to somehow avoid the police officer and still be able to cross the border. So what can I do? I can now force the network to be a bit more sophisticated, and the sophistication comes from this angle. Again, nothing changes in life. It's the same encoder network, it's the same decoder network. I just rearrange them in a smart way, right? So the student, what he did was like he took the semantic code, which is nothing but the latent space, and then he said like from the latent space I start linearly interpolating between the points. Between two latent space I can find intermediate points, right? So I find the intermediate points, and then on top of that he introduced what is called as the identity constraints, and suddenly you have this diffusion process which can also help in refining the latent space. Then you have better images. Okay, what is happening? Okay, right? So now here, for those of you who still recall the formulas of the loss function, now the idea is to again optimize the loss function here, right? So the loss function is nothing but the ID features of that person and the difference between the ID and the obtained ID. So as long as you can optimize that together, you're going to get new set of images which are much more stronger. So what does that lead to? So that leads to an improved performance here. So there are different generation of morphing approaches here. You can see that this is bona fide image number 1, bona fide number 2. So then we are combining them. With first approach, I get the landmark based approach, I get image like this, which is more similar to this person than this person. Second one is the MODIF, which is the Morgan approach that I showed before. And then here is the newly introduced approach, the one that we are talking about now. And then you have the one that I showed you in the previous slide. You see that there is a quality improvement, right? So now this image is somehow closer to both the subjects rather than the other aspects. Okay, so depending on your application, you would want to create such kind of generative content using the architectures that we have been talking about. Okay, and then what about diffusion? Is there any works on diffusion? So now comes the idea of GAN, which had some limitations, and then we said diffusion can solve some of those problems. And how can we use the diffusion for creating better attacks, better synthetic content? And the idea here is very simple again, right? So yesterday we spoke that we have this, if you take two vectors, they should be in the proximity, vector A and vector B. And now if I take all the vectors that are possible for a face recognition system, they should somehow lie in a sphere, right? If I project a globe, so all the people in the world have to live on the globe, right? So you cannot be outside of the globe. So which is exactly the similar analogy that we can use here. If I take all the embeddings of the people and I can put it on a sphere, they should be spread across somehow. Sometimes they are clustered, sometimes they are very close, sometimes they are a bit far, but they are still lying in that space. Now, as soon as I have that idea, so what I can do is that I can look for the latent vector which are closer to each other. So what I can do is I can introduce, if this is my sphere and the point lies here, another point lies here, another point lies here, right? So I can do a radius search. So I do a radius search, which means these two images come in that radius. So I can say that take the latent space of this particular image, latent space of this particular image, and then combine this one with this one, right? So I have new image here, new image here. Again, what are we doing? We are making use of the deep networks, the CNNs, to extract the embeddings, project them onto a hypersphere, and then try to combine those images that are very close to each other. Now we are not looking at the image level, but we are looking at the embedding level. And where does this lead to? This leads to another massive tool. As you can see here, there are two subjects on the bottom side, on the left side and the right side. And without even touching anything, I just let the machine do all the work, and I'm still able to get high quality images there. More convincing? So we have made use of all the networks that we learned so far. We have made use of GAN, we have made use of encoders, decoders, and then we have made use of diffusion networks here. So at this point of time, when we have such high quality image, it's very, very difficult for me to distinguish between the real and the fake images, right? So that means I should now move on to finding the detection approaches. So in the case of morphing attack detection, you have two scenarios. One scenario where I'm going to obtain a passport, so which means I only give this image and then obtain a passport through an officer, through a government agency. Second case, where I'm trying to cross the border. How many of you have crossed the borders in Europe or in US? You have crossed the borders, right? You have seen the gates that have been installed in the airports. So which means that I don't have to stop for any officer. I can put my passport, and the passport is verified automatically, and then I can pass through the gates. So everything that is electronically enabled, at least in the European Union, you can pass through that. So in this case, there are two situations. One, you can compare this image with the image that is captured from this unit, or there is an officer who is actually looking at the passport image and your image and then making a decision. And these two things that we are talking about here, they can be either machines or they can be humans. So the goal is to detect if it is synthetic image based on one image alone, that is single image morphing attack detection. And when I have a reference image, then I can compare them one to other, and then I can say this differential morphing attack detection. Okay, so where is the challenge now? The challenge is not just in detecting those kind of synthetic content, right? The current day morphing attack systems are much more sophisticated, the manipulation systems, because we suddenly have the ability of LLMs. So that means I can generate a base morph image, and now I can tell, make this person look 10 years older, make this person look 5 years younger, right? And then I can also add that, okay, make this person to have some beard, make this person to have some different hairstyle. So every time I do this, the image becomes more and more realistic. So the more it becomes realistic, the difficult it becomes to detect that. And in addition to that, there is another problem. The problem here is that I have no control over what kind of printers you are using. I have no control over what kind of cameras you are using. On top of that, within the government agencies, I have no control over how many scanners are being used. Is it from Canon? Is it from somebody else, Sony, or so on? So there can be n number of combinations there, right? So it becomes, let's say, in the computer science perspective, it becomes an NP hard problem to find a combination of all these things, right? It's numerous combination. So despite all these things, we want to create the detection systems. But then, first part of the problem we can solve somehow. You remember yesterday I told that there is this GAN approaches which can transfer the style. So if they can transfer the style, can I not transfer the style of a particular printer to a photo, a camera to a photo, which we can do that, right? So in one of the works, that is exactly what we did. We said, okay, I don't know how many printers are going to be there, but if I know some set of printers, I can transfer the style to all the images, so I can improve my training system. Okay. So here the idea is, again, if you look very closely, again everything comes down to a GAN network, right? There's a discriminator, there's a generator, and there's a noise. And the noise here is the noise that we are putting for a particular printer, for a particular scanner. Okay. So forget about the graph on the right side. I'll come back to that later on. But you get an idea that all the things that we have been learning so far can be used in practice. Okay, so that means that we had to do the detection part, right? Despite all these challenges in the synthetic content. So comes the idea of this morphing attack detection. I told you two different kind of systems can exist. One is the single image morphing when I'm applying for the passport, and the second one is when I'm actually using my passport. Okay. So what can we do? So in one of the work that we did earlier, we started looking at the color space distribution of different printers. If you look at them very closely, the color that is produced by a Canon printer for red color might be slightly different than some other printer, right? And the same applies for the the camera itself. The color gamut might change slightly. So if I can look at those pictures, so I see that here in a very subtle manner. Okay, let me just go to the next slide. Here, in the very subtle manner, I see that the information for the real image, and the morphed image changes. In the red channel, RGB channel, the one that we see on your smartphones, you see the distribution is very, very close. Same, same, and same, except for some differences maybe in this region. Agreed? Okay. So now if I just keep that one as it is and then transform it to a different color space, which is nothing but a simple mathematical transformation, and then you can see that there is a difference, there is a difference, there is a difference here. And even more pronounced difference in this case, LAB, another color space, yet another color space here. Now what can I do? Instead of looking at only 3 channels, R, G and B, I can make use of all these 12 channels, right? So I get some complementary information that one thing is not able to capture. So if I'm able to do that, what I can do, I can go back here in this network and I say that, you know what, take all these 12 channels, start reconstructing them, each of the channel independently. So every time I'm passing this 12 channel image here, multi-channel image, from one single RGB, I encode and then I further encode, further encode, further encode. That is nothing but a variational autoencoder architecture that we saw yesterday, right? If you ignore all the arrows on top, it is exactly the same. Encoder, 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 then there is a latent space, then decoder, decoder, decoder. So it can be chained the number of times you want. And then just to keep the original information intact, what I'm also passing is like I'm also passing the original image from each particular encoder network. So when I'm reconstructing this, so I'm saying also make use of the previous information. So if I make use of previous information here, 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 and here, so finally I get a final output. And this final output, if it is a perfect image which has not been manipulated at all, so the reconstruction should be very, very clean. It should be very similar to the input image, right? So now this is the same thing that we would expect, right? In any kind of system, if there is no noise added, it should reconstruct it properly. And then once I have this, once I have that final output, then again, the final part is again learning a classifier. And this classifier can be a very simple classifier, right? It could be a SVM classifier, it could be a CNN classifier, whatever is your favorite classifier. Now I can make two different decisions there. Okay, so just to give the idea one more time here, it's nothing but you are looking at the traces of morphing, and the trace of in this case it's morphing, but it could be synthetic content, it could be deepfake, it could be some other kind of manipulations. Everything that you are talking about, there should be some residual, and this residual will be zero if it is perfect reconstruction, and if there is residual because of some other processing, it will be captured here, right? And also to touch upon the fact that life is not easy, so you will have to combine multiple losses. So what we are doing here is that there are four different losses that are added. So the first one is to look at this hypersphere concept, and that is nothing but your cross entropy loss, right? You can see that it's nothing but y log y plus 1 minus y hat log of 1 minus y hat, right? Which is exactly what we have been using so far. And then there is other problem, right? The other problem is, in this world, if we have so many images, let's assume we have 1000 images, but the number of morph that I create can be 2000. At least 2000, right? Because I can combine every 500 images with second 500 images, then I get 1000. Then if I change the combination, another 1000, and so on. So what does this result to? This results to imbalanced data sets. Okay? So you have one class overly represented as compared to second class. For instance, in your COVID, so you had massive amount of chest X-rays, but you do not have so many X-rays with COVID, right? So this is a common problem. So we introduce what is called as the asymmetric loss, which is also very well known for some other tasks. And asymmetric loss introduces a new parameter, which is very simple, subtle parameter, by bumping the numbers, and that comes in this part, the eta part here to the power. So what it does is that it kind of balances the distribution, and then it tries to learn both of them equally. And then there is also this triplet mining, right? So triplet mining is again a very simple concept, which is nothing but two real images should be closer as compared to the third one. Now, those of you who have, all of you, I think, have taken the math courses in your high school. You know the triangle inequality principle, right? So the two edges will be always shorter than the two will be longer than the third one. Right? That means we are talking about 3 points, right? Which is exactly what's the idea for triplet mining. So, but you are looking at the embedding space. And then since I'm sending 12 different channels, I also want to make sure that every single channel is getting reconstructed properly. So which means I can look at pixel wise information for each of these 12 channels. And that is what is coming in the last part. So by combining all of these things, what we could achieve is that we could achieve results that are slightly better. On the left side, you see that there is one approach number A, which is trained and tested. When it is trained and tested on different schemes, so you see that the error rates are quite high, right? So for instance, if you look at this one, so if I'm training it on this particular approach, which is landmark based approach, and testing it on GAN, so I see an error rate of approximately 50%. And then by doing such a simple architecture, I can reduce the error from 60% all the way to less than 10%. Right? So now again, the GAN approaches can be used to create the content, At the same time, they can be inverted to detect the content. And another approach is here, which is another landmark based training. And then I see that the error rates also decrease consistently across all different situations. Okay, just to connect it back to the previous topic that we discussed about this error metrics, right? We spoke about this DET, ROC, and what do we want to achieve? In this case, we want to achieve the graphs as close to zero as possible, and you can see that you are able to get it very close to zero in this case. Okay, and there is also a subtle thing which we should focus about. Whenever we are optimizing two errors, we can never achieve both the errors, right? So there's a two factor optimization problem. So we have to restrict one to optimize the second one. And this is nearly impossible. So what we do is that we set a threshold of these dotted lines. You see that here, this one and this one. So what it says is that, okay, I'm willing to accept 10%, I'm willing to create inconvenience to 10% of the people, but I don't want the malicious actors to get into the system. So you're enforcing very strict thresholds. You are saying, okay, I'll allow 5%, I'll allow 10%, and in that case, you see the error rate is here. So it's around 20%, 20 point, I think 18 point some percent. Gives an idea about what we are talking about, the synthetic content detection and generation part. And now I can go a bit further, and this I'm motivating it for the talk tomorrow on explainability. And CAMs are one of the explainability methods that are very well used in deep neural networks, and these are again nothing but the gradients. So you're back propagating the gradients, and in this case we take the gradients and then we create the masks. When we do that, we see that the areas that are being used for decisions to tell that whether it's modified image or not modified image, these are the areas that are highlighted. Now, if you are carefully looking into the image, what you can see is that in different kind of approaches, the consistency is not there. So the area that is used for detecting that this is a modified image is not the same as the area that is used for detecting that it's a bona fide image or it's not a modified image. We want them to be very consistent, right? So this is an open problem. So if any of you are interested in looking at this, this would be a very nice contribution. And this is for one camera, so one approach, and the second thing is also for the similar thing for the second kind of approach. Okay, and then since I'm also talking about this first approach, now there is a nice taxonomy of all the different approaches that are available. As you can see from the taxonomy here, you see that morphing attack detection can be based on handcrafted features, they can be based on your deep features, it can be based on landmark detection, it can be based on demorphing, and so on. So in the case of this reference based DMAT, what I can do is like I can take the image and then extract the embeddings. Again, some very well known pre-trained face network. I take that, I extract the embeddings, I extract the embeddings. When I do the subtraction between them, if it is not morphed, then the difference should be very, very low. Ideally 0, but we never get 0 because today I might have taken the picture, and tomorrow when I take the second picture, there will be conditions that will change and the embeddings will also change. So there is a bit of a small threshold, and with that threshold I can create a SVM classifier and I can say that whether it's bona fide or it's morphed image. Good. Okay, so I think I have a couple of more minutes. So what I could do is now I can motivate you for another problem within the morphing attack detection. Okay, at this point of time, did you all get an idea of the generation part and also the detection part, specifically for the face recognition systems? Yeah. Okay, if you don't have any questions, then I have a second problem. So if I'm going to go to, let's assume I go to India, and then I collect all the pictures, and then I say that I want to use it in China to make the system better. Will you be happy? Yes or no? At least some heads are saying no. Okay, so then it's the same problem, right? So why would somebody be willing to give their data to improve the systems? Nobody wants to share their data. So what is the solution for this one? So what we are looking at recently is another approach which is called as federated learning, which means everybody owns their own data, only the models get updated, right? Which means I learn a model here for Indian population, I take the model with me without touching your data, and I adapt the model to the population in, let's say, in Germany, and then I update the model. Now this model can be used by both India and Germany, right? Now I can do it across all different countries without actually exchanging the data. And this has been used in the case of the morphing attack detection, where we see that, okay, what is the performance gain we get by combining all the data sets together and learning one model as compared to iteratively updating the model over different data samples. So here you see that in this picture, right? So if I zoom that one in, you see that there is a site 1 model, let's say from Rajasthan, site 2 model which is from Madhya Pradesh, site 3 model which is from Delhi. Then I can take all the data and then learn 3 different models. And once I learn all these 3 different models, I can update the global model. Now the global model, once it is stable, I can send it back to all the other people, right? So it's a two-way update we can do. So first we do one-way update from this data to this map, and then once I'm satisfied with that, I can push that model back to the independent. Okay, so are there any people aware of this being used in everyday life? Can you relate to any model that you are using every day? I'm very sure that most of you are using this model without knowing it. How many of you own Alexa? You own Alexa? You own Alexa? How many of you own iPhone? You own iPhone? You say hello Siri, you say hi Alexa, and it works, right? It works irrespective of what kind of accent I have, what kind of dialect I have. So how is that done? So you have a global model up there, and then it's fine-tuned for every single user by just looking at some data. So you have the base model, which is that global model, and then you have the fine-tuned models which are locally on your devices. So that's how it's able to recognize it. So if you want to test it out next time when some guest comes into your house, ask them to say hi Alexa. It will struggle to identify that voice for some time until it gets used to that. Okay, good. So then I opened up two data problem, and the second one is regarding the explainability. I think there's a lot of young researchers sitting here who might be looking. If you're able to do this here, you can also do it in other domains, like let's say medical domain. Only the semantic meaning will be different slightly, but you can still adapt it. Now that I have few minutes on the adversarial attacks. So what are these adversarial attacks? It's nothing but image plus noise, right? I have uh, I have this latent vector, whether it's image space or it's latent space, whatever it is. I have this one. So what I'm going to add is that I'm going to add some noise, which is epsilon here, and then as soon as I add that, the boundary gets moved. Let's forget about that part. Let's think about here, right? I have this panda, image of panda with a confidence of 57%, and this is the random noise that I'm taking. I combine this noise, this image, with this noise. When I do that, the image that you're seeing here has no physical changes at all. But suddenly what happens is that now it's referred as given, right? So with 99% confidence. So that means any image from here, I can simply flip the labels by adding this kind of noise. So if you translate the same knowledge back into the face recognition, so what exactly happens is this one, right? So I have the face image there. the clean images, which are on the left corner, the left column, and then I simply add some noise into that. Every time I add some noise, the image is still reconstructed, and sometimes you see the images are still clean. And if you increase the noise levels, then it becomes very, very bad. At this point of time, those images are not very useful. But even with the subtle noise that you are going to get, what you're going to do is that you can flip the distribution of the scores, which for instance are, let me see, which ends up like this. So I have an image, I give another image for comparison. When I do the comparison, I should get two different distributions, which is genuine versus the same person with the same person against the same person with different person. So now you see that the adding the value of this epsilon can push the scores back, which means your system is under attack, which is not, right? Make sense? Okay, so now what you can do is you can go back and retrain your whole network, whole face recognition system, and move back the scores again. But then it's still it needs a lot of retraining, right? So there are a lot of new works that are coming out in this direction, where they're not retraining the whole model, but instead they're updating the model in certain way. Okay. Okay, so that concludes. I could still talk a bit about this one, but I mean, if you really want to get into the gradient part, everything that's happening is in this formula. So this formula is the formula that we started with. You have a formula which is based on the derivatives, and then you simply keep on updating these gradients all the time. Okay.
So we can break for 3 and then we can start at 3:30.
At 3:30. I don't know if you have any questions so far. Anything on related to this adversarial attacks or morphing attacks?